Hello everyone, I'm Erik, and today I'll be presenting something titled Injecting Faithfullnes and Logic into LLMs. The title prior to this was much more epic. It was the promises and chain of thought and how they'd never delivered. So let's actually think about reasoning step by step. What is actually this reasoning that we're talking about? And what do we mean by logic and faithfulness in the vicinity of this? So logic in of itself and reasoning have been divided into a variety of tasks ranging from causal reasoning, logical reasoning, mathematical reasoning, common sense reasoning, and others. And in general, we try to formalize this as the capability to induce, apply, and compose facts and relations given the query. The ability to follow instructions is also a part of reasoning because you're able to faithfully complete a set of actions, and the ability to generalize from a given context and demonstrations, examples. So in this topic, we're going to mainly cover some... Why? Okay. Sorry? 1, 2, 3. Okay. Okay. Yeah, we're going to cover some methods for how can we do this type of reasoning, and by this type of reasoning, I again mean logical reasoning in terms of formal mathematical logic, and more like common sense soft reasoning. So, first of all, we have to talk about chain of thought reasoning, what's good about it, and why it is awful. So, this think step-by-step concept was introduced in one of the first chain of thought papers by Wei et al., and this freeform text with intermediate steps, which we'll look through a bit later, was the premise of it. Essentially, given a query, we try to decompose it into a set of intermediate reasons, and then we try to answer the question. So, why is it going through? 1, 2, okay. Yeah. So the standard prompting practice is given a question, given an answer. That's also called direct answering. And given a chain of thought, we try to list reasons, intermediate reasoning steps in common sense, like layman logic, and try to answer it. And it has been shown to be quite good. It improves the results. And as told in many of our prior presentations, we don't really know why. So let's actually talk why it is bad. So, chain of thought has massive problems. First of all, is the breakdown of intermediate steps is very ambiguous. We don't really know where the reason starts, where it ends, what does it entail, is it a sub-goal, what type of a question does it pose and does it answer? Second of all, there is this thing about unfaithfulness. You can get an answer given intermediate reasons. However, the answer does not necessarily come from that intermediate reasons. We'll see more research about this a bit later and talk about it more in depth. So, right intermediate steps, wrong final answer, wrong intermediate steps, right final answer, and so on and so forth. One very bad thing is verifiability. As a scientist, we would like to understand, are we doing good chain of thought or bad chain of thought outside of looking at accuracy? However, we don't really have very good data sets and means to understand, can we really verify if the sub-question, intermediate step, was answered correctly? That's another problem. So, yeah, as I told, we don't always pay attention to context in chain of thought application, and the longer the context gets, the worse the results get. And the length of chain is highly impactful on the data. Also, we're prone to hallucinations with this intermediate type of reasoning. So, we see like one very clear example here. There's like a very long question in the input, and the chain of thought output essentially lists a bunch of reasons. It comes to the answer of 200. However, in the very end, it says the answer is 0. Very unfaithful, very bad. And the thing is, we cannot automatically detect it, really. It's very hard. So, let's talk about verifiability a bit. So there has been a recent paper by Jacobi et al. In 2024 that chain of thought is as strong as its weakest link, where they create a data set for chain of thought where they try to verify intermediate steps. This is like one-of-a-kind data set that just recently came out. With the idea being, we try to understand, was the intermediate reason given correct? Was it factual? Was it logical? Was it relevant to the context? And they annotated a bunch of data, and it turns out that most of the models in two-class attribution, in logic attribution, and three-class attribution fall off quite drastically. You can see that the models here are a bit older. They're not like GPT-4os, because this is, I think, a research that was wrapped in 2024, but it was started in 2022. So we don't really know what would happen with the modern models, but the trend should be quite similar. Let's talk about faithfulness. So in theory, today we also heard an alternative phrasing for faithfulness, namely LLM self-consistency, but I quite like the wording of faithfulness because it induces only one thing. Is the output following from the input? As simple as that, or following the reasons given before it. That's the easiness of defining. So it has been shown that when we're trying to measure faithfulness in chain of thought, models show very large variations across a variety of tasks. And they don't really explain this variation. For example, I think we faced this example today as well. If we somehow in context say that the correct answer is always A, and it answers A, it will never tell you, yeah, because it's in my context. But it will answer correctly or incorrectly without giving you a reason. That's why we can't really measure faithfulness of how faithful it is to the context. Sometimes we rely heavily on chain of thought. Other times we kind of ignore the chain of thought reasoning, which is less than ideal. And as models become larger and more capable, they produce less faithful reasoning. So we have this like inverse proportionality across several research. Also, there's extra compute for more tokens in chain of thought, and it's not necessarily an improvement. And another study called Language Models Don't Always Say What They Think is the example I presented. Also showed that there is a big variation that in explanations and in how the model performs that can be quite misleading. This is the graph that shows that, yeah, if we do it in unbiased context and biased context, there is like a big drop-off with no chain of thought and chain of thought. And they're trying it all across Big Bench Hard, which is a quite substantially hard data set a challenging data set to master. One thing about chain of thought that should be mentioned is we can't really replace chain of thought tokens with something random. We can't put dot, dot, dot instead of all the tokens and hope that the model just has more time to do computation. That has been done as well. And it turns out the results are massively worse. So the words do matter, but which words matter, we don't know. And we can't really measure as well. That's why several methods have come across different lines of research that tries to circumvent this problem, and they introduce a problem of their own. So there is this deductive verification of chain of thought reasoning, which is the predecessor of interleaving with retrieval paper. So the idea is to write the deductive plan, break down the deductions into actions, and move on from there. There is something called React prompting. It's predecessor of tool usage, which says, let's actually create the reasons and then create an action plan. In context of tool usage, this would be, which tools should I use in succession, and let's see what observations these tools give me after the usage. Interacting with external tools and retrieving additional information, and it's more reliable at factual responses. There's chain of thought self-consistency, it's an idea that I really don't like. It's a predecessor of nothing really. It just says, let's run chain of thought 50,000 times and average whatever the answer is, and that is our answer. I don't know. I can't really give good coverage on this one. It's very popular, but also very costly. So there's least to most prompting, which is the predecessor of tree of thought-like ideas, which we're going to cover later. And it's good because it says, okay, let's divide it into sub-problems and solve each one step by step. All of these methods have quite big problems. So first of all, First of all, the chains are still not verifiable. Even if we try to deductively ask the LLM, are you thinking correctly, we still don't have a formal verification process that can deterministically say, yeah, this sub-goal was solved correctly. That is very bad. That is very bad because we just rely on LLM to intrinsically know when it's correct, and in a lot of cases we've been shown that that's not really true. The goal breakdown is also unclear because we're operating in natural text. Whatever we divide our chain of thought into, the intermediate reasons, we can't really automatically say, yeah, this is like half of the sub-goal, or like measure how hard the sub-queries are. It's dubious. And yeah, because it's stemming from chain of thought, it's still unfaithful. React has this problem of looping, where you can try to go through one tool. If it gives you an irrelevant answer, it will start looping endlessly until it obtains something reasonable, which is not a very hard problem to programmatically solve, but it's still, in theory, bad. There is a structural reasoning constraint. What do I mean by this? We divide this whole reasoning paradigm, regardless of what type of reasoning it is, into two steps: reason, act, which is, in human terms, not necessarily what you do when you see a problem. You try to divide it into sub-problems. There's like a bit more nuance and more humanesque feeling of this. And chain of thought with self-consistency is very costly. It's the same chain of thought, but done a lot of times. And the same problems emerge with least to most prompting as well. It's hard to generalize. The compositions are hard to generalize. They might be correct for one sample. They might not be correct for all the samples in a certain domain. So it's very hard to decompose as well. But there's good. So there is good in all of these methods that we can try to take. So one thing is we have this notion of state. The reinforcement learning people are rather familiar with this, where we kind of define what we're operating over. Essentially, what are the facts, relations, how are they interconnected, can we optimize them, can we change the state? And it's very good to have this. It's an idea in of itself. And it allows to pay more attention in context. Of course, one thing is that if at least trying to have some type of a planning is also good, it adds like more faithfulness and attention to the context. Trying to run the same thing several times, of course, like is ensembling mixture of experts type of idea in an untrained manner. It's more faithful, of course, because if you ask the same question 1,000 times and average out, you more or less know that's what the model is thinking. And division into sub-goals is something that we very clearly need. So let's keep this ideas for now and go into a completely different line of research. There are decoding ways that actually try to tackle reasoning as well. And there's something named context-aware decoding, which says, essentially, let's generate once without the context and once with the context. The context can be your intermediate reasons. So generate one time without the intermediate reasons, one time with the intermediate reasons, and try to calculate the divergence in between the tokens of the two outputs. That's how you guide your second decoding process. And there's DOLA that says the earlier layers of the transformer should not include the abstract reasoning capabilities. That's why the output obtained from adding a softmax on them should be quite different than if I add, if I compare them to the last layer softmax. So it's a dubious idea, but it's not bad. It shows that if we try to train the model like this, it gets more factual and less grammatical. So, and there's the inference time intervention, which says, let's find directions using attention heads based on like truthful QA performance. And essentially, that directions are vectors that show that a direction. They call it a direction of factuality. You can call it a direction that maximizes truthful QA, which they say most likely should be the same. So, of course, there are problems. Context-aware decoding is costly because you have to run the same query 2 times at least. Obviously, not perfect. And interaction with prompting is unclear. So you don't know if you add chain of thought on top, how does this type of decoding interact with it. There is DOLA, which is like layer contrasting is not obvious. It can hurt context use. You essentially say, like, at parts you don't need the context, you need to forget it. And explicitly for training, technical difficulty. So, and it can worsen the lexicon, so the grammatics get messed up because the earlier layers are like better at predicting grammatics at understanding them. And it causes more hallucinations, which is weird. So, and for inference time intervention, directions are hard to find. Direction can be very, very similar. For example, if you're looking for factuality, you might as well be looking for something that are very close to factuality, but not factuality. Essentially, plausibility is one of those directions. So, like, you're looking at what can be in here instead of what should be in here. But also, like, there's good. So one thing is faithfulness. With context-aware decoding, you explicitly condition on the fact that I generated once without the context, and now I generate to avoid that. So you're forcing yourself to be more faithful. It's tunable to attention, and it causes less hallucinations, as the facts show. It's good for knowledge conflicts. This DOLA thingy adds modularity in the sense that we kind of try to understand which part is good for grammar, which part is good for abstract reasoning, mathematical reasoning. We try to like divide it in a transformer rather physically. It's a decent idea. And this inference time intervention is something very good because what it really does is it just adds an offset vector. An offset vector can be thought that a set of offset vectors can be thought of as traversing the manifold of the embedding space that the model created. So it's actually better to have something similar to this. And it's controlled because we do know what we're exploring. And the very last thing that I want to present is faithful COT, logic LM, and explaining self-supervised logic enhanced training. So this is a complete like opposite line which relies more on symbolic AI. It says, faithful COT does the following. It says, let's ask the model to generate code and then run that code using an external solver. Obviously, it's 100% faithful because the external solver is deterministic and gives you the same answer all the time. So it's completely good. But one thing that's very bad about it is translations from natural language to formal language for programming is very, very hard. We'll cover that a bit more in depth a bit later. So generated facts can be missing. So you might as well miss some common sense fact that's not mentioned in the question context. You might miss some interrelation between the facts that's not explicitly mentioned. So there are that comes from the translation, from the auto-formalization part. And the generated facts might as well just be outdated or wrong in of itself because of hallucination. So one thing is that if you generate something that's not runnable by an external solver, you essentially are unable to complete your task. That's why fuzzy reasoning, as we call it, is impossible in this type of domains. But one thing good about it, it's faithful. It's very modular. We know this is the code. We have to run the code. Like everything is separated in terms of reasoning. It's explainable. We can say, yeah, this part of the code is responsible for this. It's very easy to interpret. And chains are kind of verifiable because we can look at the abstract syntax tree of the program or whatever it generates and say, yeah, this part did this. And verify what the actual output is, why the actual output is there, so on and so forth. So logic LM is the same idea with different solvers without breaking down the task. And it does one thing additional. It says, okay, now let's also do self-refining. If the code doesn't work, just run it until it works. The problems are the same. The generated facts might be wrong, missing. Again, you have to come up with a program that works. If you try to look into a paradigm that the model was not explicitly trained on, which we'll show later, this is sometimes even impossible. Like generating Prolog code that the model hasn't seen is very hard. Or lean code that Google so much boasts these days is non-trivial. So And the very last thing is exploring self-supervised logic enhanced training. It learns the same facts in a direct and indirect way. So you try to essentially say, yeah, create a program to come up to this fact, create a pseudocode to come up to this fact, various ways to come up to the same thing, and assuming that knowing different directions to come to the same concept will make you better at that concept during the decoding time. However, yep. Boom, boom, boom. So we don't really have the code for the last one. I think that's a major flaw. And the data heuristic that they define in their paper is a bit fuzzy. Essentially, how to choose the data, a sample for this type of exploration is unclear. But the good about this is we have more faithfulness, modularity, explainability, and chains are verifiable. So let's talk a bit about auto-formalization, which is the formal task of going from natural language to any programming language. In this particular case, I chose Lean. Lean is a theorem prover that, given a set of facts relations, mathematical facts and relations in between them, proves a certain property about the proves a certain theorem, you can say. So this is like a very old example. It says like prove that there is no function f from the set of non-negative integers into itself, such that f of n is equal to n plus 1987 for every n. And the codex output, the codex at the time of the writing was like the bigger model that was trained on code explicitly, fails rather drastically. And they have like this automated evaluation across a variety of tasks in natural language, like strategy QA, natural QA, that show that it's very not trivial to go from one to the other. So, and bridging these logical gaps left in pen and paper proofs is non-trivial, assuming that implicit context and assumptions in auto-formalization is extremely challenging. However, informalization is relatively easy. Going from code to natural language is not as hard as going the other way. It's very natural because like we can just write it out as a sentence. And translating from a strict constraint domain to a free-form domain is okay. The ambiguous variable functions can be left as is, like a function name that does not define anything but has some description can be just left as is, and you can just simply explain it. That's why it's easy. And it allows for soft reasoning. If we just reason around language, we don't necessarily need to impose, yeah, your code has to run type of a constraint, which is good. So, there is like an example of this called chain of code. We'll cover it a bit later. One thing that we have to cover is tree of thoughts. So tree of thought is this. So tree of thought is this idea of let's try to simulate BFS or any type of heuristic traversal along the problem space, where you explicitly have nodes that are assumably covering some part of the sub-question. However, it's also like, it has inherent problems coming from the whole chain of thought thingy. One thing is the breakdown of intermediate step is still ambiguous. It's text. You don't really know what the text is about if you're operating on more than 1 million automated, like, generated tree of thoughts. It allows for backtracking search. Essentially, it can do something, yet this is not a good direction. However, the way tree of thought do it is less than ideal because they ask the same LLM given the node, do you think this will lead it to a good solution? And if the answer is yes, then it continues. If the answer is no, it finishes off. And we already know that asking the LLM if it's doing good or bad is a less than ideal solution. It's better than nothing. It's worse than actually doing verification. It's very modular, so we can divide and like look at different paths the model took to arrive at a conclusion. But it's also very costly. That's why we don't see trees that are like deeper than like bigger than a depth of 3, 4, because the exponential cost of covering the tree can be very big or implausible for one sample. So now the text-heavy slide is incoming. So what do we want to avoid, how, and the potential outcomes? So We want to avoid chains that are not verifiable, goal breakdown unclear. We want to not be unfaithful. We don't want to have looping, like of reasoning. We don't want to be reasoning constrained. We don't want to derail reasoning. We want the inference to be plausible, not to be costly computationally or verifiably. We don't want hallucinations, and we don't want to be very data dependent. Like the reasoning way should be independent of the data. It should be rather generalistic. So the good ideas that we took from this is from various lines of research are the following. Let's keep a state of facts and relations. Let's explicitly state the decomposition of the task, essentially what are we solving currently. Let's explicitly have goal decompositions, essentially these are the facts that we're using, and we're using these facts to prove a certain type of subgoal. We have to be fuzzy, so we don't rely on an external solver being runnable. And we would like the stateful search with planning and backtracking. So we would like to do something like a graph traversal, while being able to say, yeah, this idea does not lead to a good solution. And we want to be able to verify if our paths explicitly were correct or incorrect. So, and the potential outcomes are this, that will be modular, verifiable, and all the world will be good, we'll solve reasoning, AGI will be solved, and we'll be happy. So, with this in mind, we created a method called Flare. It's called Faithful Logic Aided Reasoning and Exploration, which has the following paradigms that we covered before, and we kind of try to cover the bad parts of chain of thought in between. So, given a query, a natural language query, we just prompt an LLM. For now, let's have that as the reasoning, to create something called a plan, which has an explanation, explicit sections for explanation, analysis, and plans to generate code. We control for this very explicitly. We both have trained models that do this. We both have few-shot like variations of it that do this. We'll cover it a bit later. The idea is that there was a paper that said, if you do this on a couple of domains, we're able to understand what those domains are about and get the facts and relationships and the general logic of the domain better. It has been more or less like shown in a couple of papers. So after generating a plan with several components, we generate code. So which contains this aforementioned facts, relations, and the search logic. And we call this state. So I have to be a bit more clear here. It's not shown in the slides. We chose Prolog for doing this, and there was an explicit reason for choosing Prolog. Prolog inherently divides your code in a way that has facts, they call it atoms, relationships in between the facts, and any goal can be formalized as an interplay of conjunctions, disjunctions, and negations in between these facts and relations. That's why, and it also does this like explicit search DFS, although you can have like A star if you define some weights around it. You can do any type of problem traversal with this. So we do have a notion of state. However, we don't really want to produce something that's necessarily runnable. I told you that we don't want to run this code all the time. We should be able to do soft reasoning. That's why we asked the LLM to simulate what the traversal of the program would have been. So I will show you more concretely what this means on a given example, but the idea basically is, while we have the facts, relations, and we have them consistently, our program is not necessarily runnable. It doesn't have to be runnable. We just have to know what facts interplay with what other facts in what way. And then we can simulate this multi-hop, step-by-step reasoning of how to obtain the final goal. So, in essence, we do some type of a simulated traversal, and we update the state during that traversal. Essentially, if a new fact arises, we deem it not to be a hallucination, I'll tell you about it later, we add it to the state. If some fact is underutilized, we know about it. And yeah, at the very end, I also tell you how we measure faithfulness in this whole ideology. because it's DFS or like completely greedy search, we also can do like backtracking. We can say, yeah, this path does not lead to anything, and we can verify it using some Prolog external solver if you very much want to. And yeah, this leads us to the answer. Now let's actually give some example to show it how it happens better. This is like the overall view of what happens. Let's go through it. So this is your general chain of thought. Some intermediate. The question is, do all parts of aloe vera plant taste good? Which is a very natural language question. It doesn't have anything algorithmic, mathematical, but we still want to solve it. So the chain of thought will give you some intermediate reasons. Say no, and if you say now answer this, it will say yes. Bad. We have like a bunch of bad reasons that this happens. Then we have faithful chain of thought. Oh, papa, why did it raster incorrectly? Hey. So we have faithful chain of thought. It has intermediate reasons, code, and the results of the code are not parsable. That's why we don't have an answer. Not very nice. So then we have all of this. Let's show this step by step. So we have a plan which has explanation, analysis, and like plan for logically answering the question. It's just a natural task that has been shown to improve performance. We have tried our methods without this, and we have seen consistent results even without this, but we have left this just in case. So it's just whatever you have in chain of thought. Then we have the code and the search traversal. So this is like a very generic Prolog code which says aloe vera is a plant of used for medicinal and cosmetic purposes, like define our aloe vera. Then we have like it's a petroleum derived product potentially, which we can further verify if it is using some external tool very explicitly. That's why it's very good for us. And then we also have the reasoning chain. So this last line here says, in order to answer the query, we have to use the function combine. The function combine says, we have to check if aloe vera is a plant, we have to check if it's a like petroleum derived product, and then we have to check if it uses emulsifier or not. For all intents and purposes, this code must not be runnable. In this example, it is runnable, but it can be completely like obscure. And then we generate the search. So we generate several paths. The path is like one direction in depth first traversal. It can be breadth first traversal, we don't really care. And essentially we see step by step which facts does it use. Does it use them correctly? Essentially, does it skip some reasoning steps? Does it not skip some reasoning steps? That's the nice part about it. And we can explicitly say, oh, did it use this relation? Did it use this fact during the traversal? Did it add any new facts, which will be a hallucination? We can avoid that. That's very nice. And at the very end, we ask, of each path, we ask it to generate a result. So then we can do also backtracking, say, okay, redo it from this part, and it will redo it from that part. So that's the general gist of the problem that we're trying to cover. So the good part about this is how we measure this faithfulness, because I kind of promised you that we do measure it, but never mentioned how. While some of the code can be not runnable, most of the code, like 50%, 40% of the code, is still runnable. That's why we can use that subsample to explicitly generate the path and compare the outputs of each search explicitly with each other using rouge, blue, or your favorite textual comparison. We can even do something further, which we did. We did graph comparison. Is one search a subgraph of the other search, which is more strict in that type of domains? And it turns out that, I'll cover it a bit later, that the more faithful towards the original execution the thing is, the better results you get. Yeah, so that's, we do this for all samples, average it out, and obtain some results we'll show. And we also show that independent almost of the amount of in-context examples, we still have a lot of samples to operate on. So in approximately like 50 to 60% of cases, even for like a smaller 30B model, we are able to generate code. If we're able to generate code, we're able to generate trace using an external solver. Yep. So one thing is, this also allows us to detect like very perfect logic executions. we know this should have been the execution, and we compare it directly. If the similarity is very high, we can say, yeah, we're as faithful as we can get. And this also allows us to generate less perfect logic, like, yeah, a lot of hallucinations in between, a lot of skipped steps, the logic is imperfect, we can't really confirm it, don't use it. So now let's talk about results. We cover a variety of different benchmarks ranging from math problems like GSM8 K-Swamp, multi-arita Steve Aqua, multi-hop question answering, which is strategy QA, and data port subsets from Big Bench Hard that are standard, and then relation computation. One thing in this graph that you should see is that we compare against the model a bit unfairly, because Codex is a model that is explicitly trained on code. Everything else that we did might have seen something in the pre-training, but was not explicitly trained to generate code. That's why the executions are a bit unfair. So, however, we still see that our model performs rather decently, even with a bigger model that is already trained to code. What's a bit more fair is we say, okay, let's cover different different scales of models, ranging from 100B plus to 8B, and essentially compare FLAIR with Faithful COT with chain of thought. And on most of the benchmarks, we see that on models that are not explicitly trained for code, Faithful COT and methods like it fail rather majestically because the code doesn't run. And then, like, even chain of thought, which is thought to be very efficient, fails in a lot of cases. Like, it doesn't fail, but it is massively worse. We also see one very interesting trend. We say, okay, now let's measure the faithfulness. Essentially, for each of the models, we bucket the faithfulness into buckets from 04 to 06, 06, 08, and 08 to 1, and say, what is the overlapping trend? Does being more faithful to the actual search, to the actual execution, is it better? And it turns out that yes, up to some degree. So after this point, we don't see much better results. But if you're like around 80% following the general reasoning that you should have taken, then you're good. Yeah, what are the future ideas that can be taken from this? So one very interesting thing is that what if we don't use few-shot prompting, but say, let's explicitly train on the external solver's execution, take it as a golden sample, and generate something with an LLM without even giving it a few-shot, and that treating it as a negative sample if it's incorrect. And then training a model. Like, we'll be able to have a reward model that is able to say, yeah, your reasoning is correct, type of a thing, which is very nice. Then we can we use detected hallucinations or unfaithful paths for more accurate generation? So the idea would be, because we have very controlled ways to deal with these facts and relations, can we essentially say, this fact is unused, regenerate the whole tree? We haven't tested for this, but it's very interesting line to go through. Can we augment the code generation part with retrieval for better facts and relations? This is just like a general improvement, quality of life type of thing. And can we completely move away from programming languages? That's like a very big question that we had during the thing. Programming languages are good for imposing constraints onto the generation and being to formally parse and understand what are facts, relations, and everything else. But maybe we don't really need a programming language. Maybe we need a pseudocode that is able to formalize into a tree during the search or something like that. Maybe that is already a programming language, but that's an argument that is completely separate from here. That's the talk, guys. Thank you very much for listening.
I have a question. So I'm fascinated with the fact that most of the faithfulness research and the consistency, self-consistency, and all of it, including the first talk, is basically mimicking almost like a probing to reconstruct the lossy construction of the original training data, and creating that as a state, as a partial state representing, the reason.
Mm-hmm.
And when you do that, when you ask the the model about the parts of the plants being eaten, or where the lobsters live, or where do you read the books. Obviously, that's what you're tapping into. But when it comes to actual applications of LLMs right now, like the downstream tasks, primarily deal with the out-of-domain and out-of-distribution data, which means that the state construction, like, that gets tricky. So I wonder if you have tested it on those kinds of questions, and how do you approach the state building in a situation where there's much more uncertainty and there's less grounding in the actual parametric knowledge?
That's an amazing question, first of all. So I'll try to answer it step by step, ironically. So we did try to cover a bunch of the questions asked. So first of all, you're quite correct in saying that, yeah, on an unknown domain, auto-formalization is even harder. Like going from language to facts of whatever variety is very hard. And that is like one thing that I think currently even Google couldn't solve. So like they hand translate the lean things. But we did something very interesting. I hope I can go to the next slide. Give me a couple of seconds. It will work through. The idea being that because we're using pre-trained models, however, which are not explicitly fine-tuned on domains, we train on something called strategy QA. Strategy QA is a very finicky data set. It asks questions along the lines, did Aristotle use a laptop? No one in their vicinity of correct mind is going to use that type of a question in real life. However, for a human understanding, it is very easy. And it turns out that acting out this reasoning chain step by step, verifying yourselves in between, gets you better even at writing the code. Because first we generate a plan to go through the code, like we state the facts, then we confirm the facts, then we write the code, and only then we start executing with verification. So that's why, at least at this point, we have like state-of-the-art results, but I don't think the story ends there. So maybe on some obscure legal biochem dataset will be trash. But I think once the auto-formalization problem becomes like there's a breakthrough there, our method falls right in. Like just add the breakthrough and you'll be fine. Yeah, so I want to show this data set from here. So this numbers all across the different variety of methods, regardless of what type of a scaling the model has. It's like a very out-of-domain data set, like nothing that, like will Cindy Lauper use a rice pudding? Like that's something the Google search even wouldn't do properly.
But the information about the rice pudding and the person exists in the original parametric knowledge in some ways.
Yes, that's why I said if we have some biochem data that we have zero idea about, yeah, the model won't be able to solve it. However, maybe there's like this like you can try to interleave the facts with like knowledge there. We haven't tested very explicitly for that type of domains, but maybe that remains to be seen.
Thank you.
Yep. Well,
thanks for great presentation. I have a question. Do you like adjust the plan when you explore it? There is no way the plan is stuck.
So I left this as a future idea. We didn't have time to do it very explicitly, but yes, we should most likely do it. Like do some type of a self-refinement iteration over the process. We just wanted to test, does simulating search work? That was the idea. But yeah, that's definitely an idea that we should be aiming for.
Thanks a lot for the presentation and for the very extensive survey about the alternatives. So I didn't really get the part about detecting hallucinations and how are you doing that. Maybe I missed that.
Yep, sure. So essentially, let's say we have the code that we have written and the chain, like the search that comes after the code. The search is essentially a DFS that is using the facts and relations in the code. So if during this search, we somehow have a fact that is never mentioned in the code, the model is very likely hallucinating. So essentially, this is where we list our state, the facts, the relations, and everything. If during search we write something that's not here, we either came up with something grandiose and like a very new fact that should be there, that should have been there in the very first place, and it's not there, or it is hallucinated. That's like how we define the hallucination in this case.
So in a way, you are trying to say that there is a trade-off, but if there is a very small problem to solve, there is less chance or less probability for the model to fail, right?
Yeah, explicitly. We say we don't really need to run this as code. The trade-off might be that it's not 100% faithful, but we say being 80% faithful in terms of hallucinations and everything is sufficient to get a good result that is measurably faithful.
Right. And the last question, sorry.
Yep.
For too much time. Do you think having some future learning where during the actual training, before the pre-training, you can give this small plan and everything to some extent for the examples, so that the model is by default doing this.
That's a great question. I think there is a parallel work that is trying to do this, and we also try to extend this. We say, what if, two questions, what if we add this into pre-training explicitly? Chain of thought has been added to pre-training in a variety of papers. We say, what if we add planning and searching in the pre-training as well? And what if we fine-tune it by this? But we still don't have very convincing results, so I'll be on the back end of, I think it will work. That's my idea.
Which metrics you are using for estimate hallucination?
Yep, so we essentially have both very frequentist way of what's the average number of hallucinations per path that you have. I didn't show them here, but they're in the paper. And for measuring faithfulness overall, give me a sec. So we're using blue, rouge, and the graph metric. Is our search a subgraph of the original search type of a metric? So rouge is, I think, more or less the standard one that's used all across to measure this type of stuff. But rouge is kind of insufficient. That's why we have to do some tricks.
Thanks.
Thank you very much, guys.